with the kinetic theory of matter, we talked about how the temperature is really, at the atomic level, just motion of atoms, or there's a relationship there where higher temperature corresponds with more motion. Well, we have an equation that gives us a better idea of what that relationship looks like. We've got the average kinetic energy is proportional to the absolute temperature of some gas, and so we are going to work with gases on this one. Now, as we cool off, that gas is going to have less and less kinetic energy in each individual molecule. Now, the molecules all move at kind of different speeds here and have different kinetic energies, so we do have to do just an average kinetic energy. So let's examine the equation. Then we've got average kinetic energy. That's going to be equal to 3/2 times this constant called the Boltzmann constant. And we can think of this as, it's in this equation, it's basically a conversion factor, a conversion ratio between temperature and average kinetic energy. So temperature is just an artifact of that. It's a different unit for expressing average kinetic energy, essentially. So with some given temperature, we can figure out what the average kinetic energy is, or vice versa. And then if we have the average kinetic energy, we could say, well, okay, we can make an estimate of the average mass for a particle of this gas. So what would its speed be? So then let's take a look at that next. So the gas that you're most familiar with would be air, or one component of that would be oxygen. So let's find out how fast oxygen is moving at room temperature. Okay, so our equation, K, is equal to 3/2 times Kb times T. Now T, the temperature, this has to be the absolute temperature or the temperature in Kelvin. So the conversion ratio, if you don't, or the conversion equation, if you don't remember that, is the temperature in Kelvin is equal to the degrees in Celsius plus 273, roughly. So room temperature in Celsius is about 20 degrees, so we'll use a temperature in Kelvin of about 293 Kelvin for this one. So our average kinetic energy, forget to write average to begin with, is going to be 3/2 times the Boltzmann constant, which is that 1.38 times 10 to the negative 23rd. And the units there are a little weird. They're 1 per Kelvin, or Kelvin to the negative 1 power. Oops, it's joules per Kelvin, my mistake there, joules per Kelvin. And then the temperature is going to be 293 Kelvin. So we get our K average is going to be equal, in this case, to, whoops, I lost my spot. Okay, 6.07 times 10 to the negative 21st joules. So not much kinetic energy for an average particle of oxygen. So now let's go back to what we know about kinetic energy from before. That kinetic energy is equal to 1/2 times mass times the speed squared. So we're going to use this value that we just calculated for our kinetic energy. We're going to have to figure out what the mass of a particle of oxygen would be in this step. So we'll use 6.07 times 10 to the negative 21 joules is equal to 1/2 times the mass. Whoops. But we want a value for the mass. Well, I know that if you've taken a chemistry class, you would have worked with this before. Otherwise, we know that there's this definition for a number of items called the mole. And so the periodic table has information about the mass of a mole of all these different items. So for oxygen, oxygen comes in pairs. We have O2 is how oxygen as a gas is usually going to be found. So this has a mass of 32, and that's grams per mole. Okay, so 32 grams, that's the same as 0.032 kilograms, but I don't want for a mole of oxygen, I want for just one molecule of oxygen. So we'll divide that by the number of oxygen molecules in a mole, which is just Avogadro's number, 6.02 times 10 to the 23rd times V squared. And so when we do this calculation, we'll solve for V, and we find in this one that the V, this is average velocity, is equal to 478 meters per second for an oxygen molecule. You're surrounded by oxygen molecules that are pummeling you in the face at 478 meters per second right now. So how come it doesn't feel painful or windy? 478 meters per second, that's hugely fast. That's faster than the speed of sound in air. So how is this not extremely harmful for you? Well, we have all these molecules that are moving in different directions. So any individual impact isn't going to be even noticeable because the mass is so ridiculously small. If we had a huge group of these all hit you at the same time at 478 meters per second in the same direction, we definitely feel that. But with all of them moving in random directions, you get a collision in one direction, and a collision in another direction, and a collision in a different direction. They kind of balance each other. And they're not all synchronized, so we don't feel this huge effect from them all at once. Now, if we want to do this more generally, we have that equation K average is equal to 3/2 times the Boltzmann constant times the absolute temperature. And we also know K is equal to 1/2 mv squared. So we can set these two equations equal to each other and derive a general equation for that. And we'll talk about that a little bit more in the next video.